I welcome you to the second video on the beautiful Grover's algorithm. Ten ten ten! In this video, we will be addressing two key questions. Number 1. How many Grover rotations do we need to achieve our desired output with a very high probability? Number 2. How do we create the circuit for Grover algorithm? To that end, we will first create circuit for each component separately and then combine these circuits to form the complete algorithm's circuit. The previous video provided an overview of the Grover's algorithm from a bird eye perspective. In contrast, this video takes a deep dive into the algorithm details, just like this little fish. Let's quickly revisit the problem definition. You are provided a function f that takes n bits as input and yields a single bit output. You can think of the function as producing either a true or a false output. Our objective is to find a specific input x for which the function returns true. It is important to note that our input space is huge, encompassing a total of 2 raised to power n inputs, also denoted as capital N. This represents an exponential input space. The function might yield a true output for a very small subset of its inputs. Consequently, this problem is sometimes referred to as finding a needle in a haystack. In order to fully comprehend the algorithm, we must define the terminologies being used. Do not worry, these definitions will be made clear through an example. Let's define a set A which contains all inputs yielding a true output. Here is the example we will be using to clarify our definitions. This example has 8 possible inputs, out of which 2 are yielding true. According to this example, our set A will have inputs 0, 1, 0 and 1, 0, 0, as only these inputs yield a true output. Next, we will define set B containing all inputs yielding a false output. For our example, that set will contain 0, 0, 0, 0, 0, 1, 0, 1, 1 and all other inputs yielding a false result. Now we represent the cardinality or size of these sets with a small a and a small b respectively. In our example, the cardinality of set A is 2 and the cardinality of set B is 6. We define ket A as an equal superposition of all the inputs of set A. As the cardinality of set A is small a, therefore amplitude of each input in ket A will be 1 over square root of small a. In our example, the amplitude of each input in ket A will be 1 over square root of 2. Similarly, ket B is an equal superposition of all the inputs in set B. Thus, in this case, the amplitude of each input will be 1 over square root of small b, which is equal to 6 in our example. Finally, we define cat h as an equal superposition of all the inputs. Now here is an interesting fact. We can rewrite cat h in terms of cat a and cat b. So cat h is equals to the square root of small a over capital N times cat a plus the square root of small b over capital N times cat b. You can easily see that these two definitions of cat h are exactly the same. I have provided my calculations in the margins for you, so in case of any doubt, you can refer to them. In our example, cat h will be 1 over square root of 8 times all superpositions of x. This is exactly the same as square root of 2 over 8 times cat a plus square root of 6 over 8 times cat b. We are done with our definitions and now can use those definitions to calculate different things. Let's quickly recall Grover rotation from the last video. We have our cat A and cat B both lying on the unit circle. Furthermore, they are orthogonal to each other, making a 90-degree angle. Then we have our vector cat h, which lies between cat A and cat B. The angle between cat h and cat B is theta. At the start of the algorithm, we set register x equals to cat h. If we measure our register right now, we can randomly get any input as all inputs have the same probability of being measured. So to increase the probability of measuring inputs from set A, we perform Grover rotations. A Grover rotation consists of two steps. Firstly, we do reflection about cat B. Let's call it R sub B. Reflection produces a mirror image of register X where the mirror is placed on cat B. The red vector represents this reflection. The register X now hold this reflected vector. The second step of Grover rotation is that we do a reflection about cat H. Let's call it R sub H. This time our mirror is placed on cat H. The result of this reflection is the orange vector, which is now stored in register X. If we measure our register X now, we may measure input from set A with a higher probability, as now our register X is closer to cat A. Note that after one rotation, our theta is changed to theta plus 2 theta. Similarly, after two Grover rotations, our theta is updated to theta plus 2 times 2 theta. Thus, after k Grover rotation, theta will be theta plus 2 times k theta. Please remember this, as we will be using it next. Let's calculate the value of theta. As stated previously, we can write cat h in terms of cat A and cat B. Furthermore, we can also express cat h in polar coordinates, since it lies on the unit circle. Hence, cat h can also be represented as sine theta times cat A plus cos theta times cat B. From these two equations involving cat h, we can deduce that sine theta is equals to the square root of small a divided by capital N. You might know the small angle approximation, where for very small theta, sine theta is approximately equals to theta. As n is very large and small a is small, so we can use small angle approximation here. You can refer to the Wikipedia article for more details on this topic. Thus, using small angle approximation, our theta is equal to the square root of A divided by capital N. Please save this important result in your memory as I will need to refer it later. Now we have enough background knowledge to answer the question, how many Grover rotations do we need? In other words, what will be the value of K? We already know that K Grover rotation change our angle between register X and cat B to theta plus 2 times K theta. Thus, we can write the content of register X after K Grover rotations in polar coordinates as sine theta plus 2 times K theta cat A plus cos theta plus 2 times K theta cat B. Our aim is to measure cat A with one probability. We know that the probability is the square of amplitude. Therefore, we scale the amplitude of cat A and equate it to 1. Solving this equation will give us the value of K. To solve it, we first take the square root of both sides and then move the sine term to the other side. We know that the inverse of sine of 1 is pi over 2. Solving it further give us K is equals to pi by 4 theta minus 1 over 2. Now we can use the value of theta that we have calculated earlier and replace it in this equation. Thus, our K will become pi by 4 times square root of n over small a minus 1 over 2. In case we do not know the value of small a, we should replace it with 1. Note that K is the number of rotations which cannot be in fractions. So, we can rewrite K as the floor of pi by 4 times the square root of n over small a, where a could be equals to 1. After K rotations, we can measure our inputs from set A with a very high probability. Now let's create a quantum circuit for reflection about cat B. Here we have register X situated between cat A and cat B. We can express it in the basis of cat A and cat B as delta times cat A plus gamma times cat B. You might be familiar with the parallelogram rule for vector addition. When we want to add two vectors, we place their initial points at the origin, then construct a parallelogram based on their magnitudes. The sum of these vectors correspond to the diagonal of the parallelogram. In our case, the length of parallelogram sides are delta times cat A and gamma times cat B, while their sum form the diagonal, which is the register X. Now let's consider changing the direction of cat A by multiplying it with minus delta. This will result in a creation of new parallelogram below cat B. If we add minus delta times cat A and gamma times cat B using the parallelogram rule, their sum will yield the desired reflection. In general, we can state that we can reflect cat mu about cat pi by changing the sign of its components orthogonal to cat pi. In our specific scenario, cat A was orthogonal to cat B, so we change its sign accordingly. We will use this rule again later, so please make a mental note about it. We have seen graphically what we want to achieve to create reflection about ket P. But how can we achieve this reflection using a matrix transformation? Let's consider a matrix with diagonal entries being -1, while the rest of the entries are all zeros. When we multiply this matrix with ket 0, the result becomes minus ket 0. This is due to the minus at the 0th location on the diagonal. Similarly, when we multiply this matrix with ket 1, we obtain minus ket 1 due to the 1 located at the first location of the diagonal. Likewise, if we multiply it with ket I, our result will be minus ket I thanks to the minus at the ith location on the diagonal. Generally, a matrix like this will flip the sign of any input ket x to minus ket x. However, in our scenario, we want to change the sign only if an input belongs to set A. Remember, set A consists of inputs for which the function f returns 1. This objective can be met by using a diagonal matrix with entries -1 raised to the power of f0, -1 raised to the power f1, -1 raised to the power f2, and the last entry being -1 raised to the power f of 2 raised to power n-1. Clearly, if we multiply this matrix with ket x, it will alter the sign only when f of x evaluates to true. So, we have achieved our desired matrix. Now, let's create a unitary function that represents this matrix. In Simon's algorithm, we utilized a unitary function uf that takes ket x and ket y as inputs. The result of this unitary operator is ket x times ket of f of x exclusive OR with ket y. This unitary operator can simulate the effect of our matrix if we give input of ket x and ket minus to this unitary operator. The output of the unitary operator will be -1 raised to power f of x times ket x, ket minus. However, we are interested only in ket x component and we can simply disregard ket minus. Note, ket minus is equals to ket 0 minus ket 1 divided by square root of 2. It is straightforward to create the quantum circuit to reflect about ket P using UF. Here it is. You might be wondering how to construct the quantum circuit for UF. Well, that depends on our function f. In the upcoming video, we will work through some examples and create different UF circuits. Let's now confirm that UF indeed generates the expected output. We feed the input ket x and ket minus into the UF function. Then we expand it using its definition. Our output becomes ket x tensor product with ket of f of x exclusive R ket minus. Now there are two cases to consider. Case 1. When f of x returns 0. In this scenario, f of x exclusive OR ket minus becomes 0 exclusive OR ket minus. Let's substitute ket minus with its definition. Subsequently, replace ket 0 with the vector 1 0 and ket 1 with the vector 0 1. We now apply exclusive OR between 0 and each element of these vectors. Our final result is ket minus. Therefore, when f of x is 0, our sign remains unchanged. Case 2. When f of x returns 1. Now f of x exclusive OR ket minus becomes 1 exclusive OR ket minus. Again, substitute ket minus with its definition. Subsequently, replace ket 0 with vector 1 0 and ket 1 with vector 0 1. When we exclusive OR the elements of these vectors with 1, the calculation yield the negation of ket minus. Consequently, when f of x is 1, our sign flips, which matches our desired output. This proves that UF works as we claimed. Finally, we need to design a quantum circuit for reflecting x about ket h. Once again, we will apply our rule, which is we can reflect ket mu about ket pi by changing the sign of its components orthogonal to ket pi. However, it is not immediately obvious how to identify the components that are orthogonal to ket h in register X. To overcome this challenge, here is a clever 3-step trick. Step 1. Map all components of ket h to ket 0. Step 2. Reflect about ket 0 using the rule. Step 3. Undo step 1 by mapping ket 0 back to ket h. The first step can be executed using Hadamard gates, as a Hadamard gate is its own inverse. In the second step, we need to negate the sign of each component orthogonal to ket 0. Interestingly, everything except ket 0 is orthogonal to ket 0. This means that our diagonal matrix will have 1 at its 0th entry, while the rest of the diagonal will contain -1. We will refer to the unitary operator implementing this diagonal matrix as U0. The final step can once again be implemented using Hadamard gates, as an Hadamard gate is inverse of itself. Here is the quantum circuit for this 3-step approach. The circuit for step 1 consists of Hadamard gates. The circuit for step 2 depends on the size of input. While we will explore its example in the upcoming video, for now let's depict it as a block. The final step can also be realized using Hadamard gates. Now we have created different circuits of components of Grover's algorithm, and we can combine them to create a quantum circuit for the whole algorithm. To that end, on the left hand side is our algorithm, whereas we construct our circuit on the right hand side. Step 1 involves creating an equal superposition and storing it in register X. To create quantum circuit for this step, we feed ket 0 as input to n Hadamard gates. Step 2 revolves around reflecting register X about ket B. This is achieved by feeding register X and ket minus into the UF block. Step 3 entails reflecting X about ket H. The quantum circuit for this step is generated using the 3-step approach we discussed earlier. Step 4 involves repeating step 2 and step 3 k times, where k equals to the floor of pi by 4 times the square root of n over small a. If the value of small a is unknown, we can consider it as 1. Our Grover rotation is highlighted above, and we have repeated it again below for the second instance. Similarly, we need to repeat this circuit k times for k Grover rotations. And that concludes this video. In the upcoming video, we will do detailed examples of Grover's algorithm, first solving it manually and then employing Qiskit simulators. So we will program and we will also solve it by hand. I am looking forward for your continuous presence. Until then, auf Wiedersehen. Tschüss.